Brian Anderson's from UC Davis. No, so yeah, we work with Brian at Granite Canyon. He's a longtime swamp partner. He and Bryn Phillips have been key components to the SPOT program, so the Surface or Stream Pollutions and Trends program. So with that, I'll hand it over to Brian and his slides. Thank you.
Is that for me or for Greg? Okay, thank you. So yeah, Brian Anderson with UC Davis. I put just my name on the slide because I made the slide, but there's obviously a lot of other people involved with the Stream Pollution Trends program. I'm not going to list all their names, but people representing a bunch of different agencies are collaborating on this program as well. And so what I'm going to try to do is summarize data over the last 6 or 7 years of the program and try to focus on how we're trying to collaborate with other people with the same goal in this program and sort of focus on how we're trying to build those collaborations to answer questions about water quality in California. So part of our emphasis is dictated by the fact that there's lots of surface water toxicity in California, and we did a summary report of all the swamp data, decades worth of swamp data. We published it a few years ago now, but it showed basically half of the samples sampled statewide were toxic to one or another species. And when you actually look at the data, when you look at the chemistry data and you look at the correlative data and the TIE data, you see that a lot of the toxicity is driven by pesticides. So I'm going to sort of emphasize the pesticide story today because it's probably the most important one in terms of causing impacts in California. It's not what the only thing that SPOT works on, but that's going to be the emphasis for today. And part of this is, what I want to look at is this idea that we have impaired water body listings in California for pesticides a lot of times. And a lot of times we find that we're behind the ball because they're listed for certain classes of pesticides that are really no longer being used. We've evolved into newer classes of pesticides, and we're always playing this game of trying to catch up with that. And that's one thing we're trying to do in this program is collaborate more to get ahead of that cycle, and I'll talk about how we're trying to do that. And the other point I want to make is that we know from intensive studies and correlative studies that pesticide toxicity in laboratory tests also correlate with impacts to macroinvertebrate communities in receiving systems. So I know there's some debate on that, but I would say the data is pretty convincing. I'll show you a little bit more recent data on that. And the reason we care about that is because we have declines in insect communities, and this is basically related to terrestrial insects, but also aquatic stages that lead to terrestrial insects. So these are declining worldwide. And I'm not trying to say it's only related to pesticides, but pesticides are playing a role in the habitat destruction and, exacerbated by climate change. But we know pesticides are playing a role in this process, and we're sort of trying to focus on that because we think it's something that we can fix if we put more intensive effort into it. And so one example I want to give here, and this is from our data in the Stream Pollution Trends program. And in a second, I'll explain give you a little better detail of what we're doing in this program. But this is showing amphipod survival in laboratory toxicity tests. So these are dead animals in beakers from samples that we've collected out in the field. And we're focused on this program largely on sediment toxicity and sediment contaminants because the majority of the contaminants that we're working with now absorb the sediments. So that's this axis, and then the x-axis is the CSCI score, which is the California Stream Condition Index, which is a summary of a bunch of different metrics that look at benthic communities in California streams. And you see as you have lower percent survival, you have this area down here where you have lower index scores, and that means they're hammered benthos. So there is a relationship here, and we've just recently done an expansion of this database by combining several different bioassessment programs, stormwater monitoring programs in Southern California and the Perennial Streams Program, which is a statewide swamp program. And when you look at a much larger N, this relationship is much better. So it's a really strong correlation. And furthermore, this correlation here in our laboratory tests correlates strongly with pesticides and sediments, in particular pyrethroid pesticides, and we get the same negative correlation between pesticides and the CSCI score. So that's just sort of one example where we're trying to integrate two different state programs to get a better idea of what's impacting macroinvertebrate communities statewide. And so we're trying to build on this so eventually we can get at what's causing macroinvertebrate impacts statewide. We don't have that answer yet. And these are just correlative studies, but they'll allow us to develop testable hypotheses as we develop this database and hopefully, get a stronger answer so that we can go after the source. So this is the gist of what we do in the SPOT program. It's a Stream Pollution Trends program, and it's devoted to trend analysis statewide. So we have 100 sites statewide, 50 of which we go to every year, and the other 50 rotate. So in any one year, we go to 75 sites. We measure toxicity in sediments with these two species. And I want to point out these two species are completely relevant to California streams because these genera occur in our water bodies statewide. So we can relate this to in-stream benthos. And we have a whole bunch of analytes. We measure a bunch of different pesticides, legacy pesticides and current use pesticides. We're trying to emphasize current use pesticides more. And then we've recently also added in fipronil as a current use pesticide. And we also measure cyanotoxins in sediments. So that's the gist of our experimental design. And the whole idea here is that we go back to the same sites year after year after year so that we can look at changing trends in contaminants and toxicity associated with that. So this is an example of one of the questions, two of the questions we're trying to answer in the program and some data that are directed towards those answers. So one is that we look at, we can see that there are increasing concentrations of pyrethroids in sediments over time as part of this program. And that's over on the left-hand graph. Then we also see that during that same time period, we see an increase in the detections of pyrethroids in sediments over time. So one other attribute of this program is we're looking at land use associated with the watersheds where we're sampling, and we can relate that to the contamination and later on to the toxicity. So we see with pyrethroids, they're dominated in urban landscapes. So watersheds that are influenced by urban landscapes. And one reason that's important, so what we're trying to do now is we know what the source of pyrethroids are, and there are regulations that have been implemented by DPR to try to limit loading of pyrethroids into urban watersheds. So one other example of a collaboration is collaborating with Department of Pesticide Regulation to look at changes in pyrethroids in sediments as a consequence of DPR's regulations to reduce loading of pesticides in urban landscapes. So they basically have label restrictions that are trying to restrict commercial applications of pyrethroids in these urban watersheds. And what we can see is another attribute of SPOT's database. We can see that these are pyrethroid concentrations expressed as TU, so it's relative to their toxicity to amphipods. It's really not changing in the time period since those label restrictions have been implemented. So it looks to us like, at least thus far, they're not working. And then this blue line here is amphipod survival, and it's also showing it's not really changing. And we're also measuring fipronil as a chemical of emerging concern. So this is just another example of how we can collaborate with another statewide program that's regulating pesticides to get a little more data to see whether or not their regulations are having any influence thus far on a pesticide we know is a pesticide of concern in California. So I just threw it in the slide because I wanted to let you know we're not only looking at pesticides and sediments, we also measure metals and a bunch of different organic chemicals as well as cyanotoxins. And so this just shows you looking at a sum of a bunch of different metals, the most important metals for toxicity, we're not really seeing any changing trend in metal concentrations. In fact, you can see these are also more influenced in urban landscapes. So these are the urban watersheds. We have higher concentrations of metals in these. And one reason this is important is we can take this data set and we can distill it down to look at something like copper, which is also being regulated in California. Copper and brake pads are being phased out. So we can see whether or not those regulations are going to affect sediment concentrations in copper over time as those are implemented. So that's another strength of this project. And another question we're trying to answer is just basically what's causing the problem. And the problem in this case is defined as dead amphipods in our test beakers. And so these are laboratory toxicity tests. And you can see the relationship between perithroids and survival is such that as you increase perithroid concentrations, you get more amphipod mortality, lower amphipod survival. So we can answer this question, and this will come up later as we talk about solutions. Then we can also confirm this further. So these are results of experiments conducted with amphipods at 2 different temperatures. So the standard temperature is 23 degrees, but we also test them at 15 degrees. And these are the results of the same samples tested at 2 different temperatures. And you can see there's a big increase in amphipod mortality or a decrease in amphipod survival at the lower test temperature. And that's because perithroids are more toxic at lower temperatures because the animals don't metabolize them. So they're just in the animals longer. So we're using this data just to confirm the problem, the idea that perithroids are a problem chemical in California watersheds. And then we're also trying to be proactive here so that we're adapting the program to look at new chemicals of emerging concern. And I'm going to talk about that concept a little bit more in a couple more slides. But this is an example of a pesticide that's on most people's CEC list. It's fipronil. It's used in urban, it's licensed for urban applications. And we can see over the 2 years when we started monitoring it, both the concentrations and the detections are increasing over time. And these are within concentrations that are toxic to one of our test organisms. So we can see for this particular CEC, this is something that's going to be a problem as time goes on. And we're predicting we're going to start seeing 303D listings based on fipronil related to toxicity in California watersheds. So this is something that's going to be on our list of regulatory problems as time goes on. And then I'm including this other group of pesticide. This is an example of one of the neonicotinoids. This isn't on anybody's CEC list yet. And it should be, because if you look at just the use data for cropping, for agriculture nationwide, the concentrations are skyrocketing. So what we're trying to do in this program now is, and again, this is in collaboration with DPR, who are regulating these chemicals, is to start adding this to our suite of pesticides that we're going to start monitoring in this program. This is one's a little bit different because the neonicotinoids are so soluble, they don't end up in sediment. So we need to adapt to monitor in water if we want to capture it. So that's one thing we're in the process of adapting the program so that we can add this in collaboration with DPR monitoring. And the idea there is we're trying to take advantage of the fact that DPR is going to a bunch of sites that line up with our spot site throughout the state, so we can get more bang for our buck by adding toxicity testing in a water column and combining that with DPR's chemistry data. So I just want to get back to this idea of contaminants of emerging concern, and one thing that's occurred to us more and more as time goes on is that we have this never-ending treadmill of pesticide problems in California. And we started with organochlorines. My career has spanned all of these. And we went to organophosphates, then perithroids, then the phenylpyrazoles, and now the neonicotinoids. But if you look at CEC lists, we're not even talking about these newer classes of pesticides yet, but we should be, because they probably already are a problem in our watersheds. We just haven't started monitoring them yet. And what we'd really like to do is be a little more nimble and a little more proactive about being quicker with our data so that we don't always have this lag where we're always playing catch up. And so that's one of the big goals of this program, is to try to work with other monitoring agencies just to get data quicker so that we can react quicker. And hopefully we're going to get to a point where we're going to have source control sooner before we start seeing these chemicals in our watershed. That's going to be a tough one with something like the neonicotinoids, because they're so soluble and they're persistent enough that we're going to be seeing them over time. How am I doing for time? Okay, you kind of freaked me out before when you. Yeah, okay. So that's all I wanted to really say about that. And this is just a summary of what we're doing with DPR. We're kind of working with them on a bunch of different levels, but we have our intensive sites that we're looking at to try to see whether or not the pre-thread label restrictions are having an effect. And then we're also working with the DPR's agriculture monitoring group to add our toxicity testing to their water monitoring, so we can take a look at some of these newer pesticide groups, toxicity related to these newer pesticide groups in agricultural watersheds. And the reason this is important is because there are existing irrigated lands monitoring programs that are using sort of traditional EPA 3 species testing, but they're sort of missing the picture if they're not evolving their test organisms so that they're the ones that are appropriately sensitive to the new classes of pesticides. So this is just trying to take advantage of DPR chemistry so we can push this process along so that these monitoring programs will evolve to characterize risk a little more correctly or accurately. And then another example I wanted to talk about of collaborations is we're not only about trying to point out problems, but we're working on practices to reduce loading of pesticides in an urban and ag watersheds. And then the idea here is, the better thing is that these pesticides don't end up in watersheds in the first place. But it's our view that for now, people are going to hate ants, and they're going to spray around their houses. And everybody's going to want perfect produce, and so we're going to have pesticides in agricultural watersheds until the people of California sort of change their viewpoint on this. We're assuming that we're going to continue to have pesticides in runoff. And so these practices are designed to sort of, when you get to that point, they're running off in stormwater, you can implement bioswales in parking lots. So these are an example of some bioswales in the city of Salinas that we studied. And these things work phenomenally well. They reduce 90 to 100% of the load of most classes of contaminants, including pesticides. The one thing they don't work with are the phenylpyrazoles. We got real variable results with those, and we think it's because of the variable solubility, the more moderate solubility of that class of pesticide. Our guess is they're not going to work for neonicotinoids at all because of their solubility. And then same sort of studies in agricultural systems, vegetative treatment systems do the same thing. 95 to 100% of most classes of pesticides can be removed just by filtering water through vegetative treatment systems before it runs off in the receiving systems. Again, we're having to fine tune those practices a little bit to polish off the residual pesticides that are still causing surface water toxicity. But these types of studies are also in collaboration with DPR and other state bond sources and EPA, among others. So this is just an example of where you get to the point where you have the data pointing at the problem, and then you can use that data to direct it right at on-the-ground solutions that'll remove these chemicals from systems. And so where we're going with this is trying to expand these to lower down in watersheds. So I just put this example because this is a sort of preliminary project that we're working on now in Orcutt Creek, which is in the lower Central Coast area. And this is one of the most polluted ag drains in the state, and it's proximate to the Santa Maria River estuary. So this is just a fire hose of pesticides going right into a system that's a small estuary on the Central Coast. And again, this is the same sort of thing where we're getting, it's collaborative projects with counties and with DPR, with EPA to try to put large-scale filtering systems for their treatment wetlands, basically for removing pesticides and associated toxicity down at the base of some of these larger watersheds. All right, so I'm almost done here. The last thing I wanted to point out was some recent work we've been doing, working with Rich Fadness in the Region 1 Regional Board and Rosalina Hrutsova, who's an algal taxonomist at Cal State San Marcos. And these are cyanobacters that produce toxins. So this particular one is called formidium, and Rich just told me he collected these in a couple sites in the Russian River as a consequence of some dog deaths in this system. And so their question was, are these things toxic to our standard test organisms? And the toxins they produce, anatoxin A, for example, it's a neurotoxin, and it binds to the same receptor as imidacloprid on insects. So our question is it toxic to standard toxicity test species? And this is important because not only can this affect our statewide monitoring of our toxicity test results, but it can affect our bioassessment data, because if these things are toxic to our test organisms, we know those correlate to components of the macroinvertebrate communities. So we're kind of at the preliminary stages of testing with this. We got cultures from Rosalina that were originally collected from the field by Rich and brought them into our laboratory and just siphoned the water off and exposed them to some water fleas. And basically everything died in a couple of days. So we know they're highly toxic, but you can also see that the concentrations here of anatoxin A, they're high. And this is in a 25% dilution. So these are parts per billion concentrations of anatoxin A. And if it's anything like imidacloprid's toxic around low 2 part per billion, 1 to 2 part per billion range. So if it has the same mode of action, we're way above that. So we're in the process of now trying to expand the study to just do a dilution series with our standard test species with these 3 different cultures of formidium, just to see where the toxicity thresholds are. And this is going to be important for us if the concentrations are comparable to what we see in the field, because then we know we've got some other chemical of concern that's going to be potentially affecting ecosystems. And then I think my last slide is this one, which is just sort of reinforcing the idea that we're trying to expand our collaborations in the program, both with DPR for the intensive site studies, and we're looking at CDCs. We've got these algal toxin collaborations going on with Cal State San Marcos and Cal State Monterey Bay. We're trying to expand the integrating our data with the bioassessment program so we can get at what's causing impacts to macroinvertebrate communities. And these are some of the other areas where we're trying to expand our collaborations. I think that was it, and I'll stop there and take any questions. Thank you. Do you have any questions? Do I have time for questions?
Yes.
Yeah.
All right.
Okay, so my question.
Neonicotinoids. Yeah, so what I mainly meant is we have this, the treadmill more is that we register new pesticides for use. They start using them for whatever application, for urban or agricultural applications. And then they eventually end up in watersheds. And we have monitoring where we eventually start detecting them, and we do studies, forensic studies, to show that they're they're causing a problem. And then after a certain amount of years go by, we list water bodies due to these pesticides, and then we start to regulate them. In the meantime, we've got new pesticides that are coming in doing the same thing. So there's this constant process. So that's what I was referring to, is trying to just address that process, though, so that we're not being so reactionary and being more proactive about it. Yeah. Terry?
So two things. One, that can be solved, that pesticide problem can be solved, by EPA getting the FIFRA folks, the Federal Insecticide and Fungus, I can't remember what it is, but the guys that do the registration for the pesticides, and the Clean Water Act that does the, the side that basically identifies problems and tries to fix them.
Yeah.
And so there's been a long effort for those two groups to try to work together, and it hasn't been fruitful. But I think it's beginning to change a little bit. I think there's more communication between those two sides of the EPA house. My question to you was the work that you're doing on the formidian.
Yeah.
Are you going to publish that soon? Because the reason I ask is that EPA is in the process of developing recreational criteria for microcystis.
Yeah.
And I believe anatoxin also, and I think there's a dearth of information. So if you are going to come up with some NOx or low-X, that would be very, very useful.
Yeah, so that's our plan. So the follow-up experiment started on Monday, and I don't know what's happening. Those are the cultures were older cultures, and this is all work for free. So, but if we do get publishable results, we're definitely going to have chemistry to go along with it. So if the story makes sense, then we'll definitely publish it, and we'll make the data available before we publish it if it's helpful.
About halfway through your talk, you had a bar graph for imidacloprid USGS data.
Yeah.
So in the last 4 years or so, some new crop showed up, and I just wondered if you knew do you know what the green is offhand? What crop that is?
Yeah, no, I don't. I didn't include that information.
Okay, no problem.
But my guess is, did somebody say soybeans? Yeah, that's probably right, because they really dominate in the Midwest.
Okay.
Yeah. The other question with them is, it's not clear to me how much they're being used in the urban environment, but I guess, Mike, they are registered for use in urban applications, right? Yeah.
So my question, is it my turn or somebody else's?
How are you?
Okay.
Okay.
So I guess I have a more of a hypothetical question about the toxicity test. When you're actually running this kind of test, so you're looking at this sort of a more of acute survivorship, or is another way of looking at it is, would you look at their say the longer term population dynamics effect, say not actually immediate killing effect, but also some of these toxic material or the toxins will affect their reproduction capabilities and their survivorship or their growth patterns that will affect in the longer term the population dynamics of certain aquatic fauna or even in other things too. So would you look at that?
Yeah, thanks for asking that question. So in the two sort of standard sediment tests that we do, we incorporate growth and survival. And with the insect, the chironomid, which is a fly larvae in an aquatic stage of a fly, that's the more important component. I didn't show any of that data because we only started doing that a couple of years ago. But when I mentioned that we had these strong correlations with the macroinvertebrate with the CSCI, which is that metric, that correlates more strongly with amphipod survival in our tests than it does with amphipod growth in our laboratory toxicity tests than it does with amphipod survival. But it's an important question because it really is important for the neonicotinoids because their effects are more chronic effects. They bind to the neuroreceptors irreversibly, and the data are showing that relative to like 10-day survival, something like a 40-day analysis of the insect's ability to metamorphose and fly away, that is a much more sensitive indicator than survival or growth. So it's important. We have to kind of balance that with the practicality of a routine program where we're testing 100 sites a year. You have to kind of compromise a little bit on how much chronic effects you can look at. But it's a really good point. I have to go. One more question.
So back to the question on the cyanotoxins. The focus here is on anatoxin A, but microcystin tends to be more widespread in higher concentrations. Are you going to focus on that in your later studies?
Yeah, so thank you for asking that question. We do measure microcystin in sediment. It's a hepatotoxin, so it's not something that we expect to be acutely toxic to our little invertebrate test organisms. It's more of a concern because it bioaccumulates and it can affect the liver in higher level organisms. I think there are some studies though that are showing that it has population level effects like on zooplankton. That's another one that we do for free. So we're a little bit, we're careful about how much we bite off on it. We're doing that in collaboration with a university group at Cal State Monterey Bay. So right now it's strictly monitoring, although we are doing some laboratory bioaccumulation experiments with that coronamid just to demonstrate that there's a route of uptake that could affect, say, fish or higher level organisms later on. So that's sort of the one thing that we are working on.
Thank you, Brian.